So today the question is on the transmission lines. As I introduced in the lecture, I think this is one of the simplest parts of the whole subject because essentially you are just going to apply some formulas to calculate the electrical parameters. All right, so there is no any technical difficulty. What you need to do is to be careful with the unit of these formulas because essentially for the L and the C, what you are going to calculate is the inductance and the capacitance, which are respectively in Henry and Faraday units. However, for power grid calculation, we need the value of impedance. So you have to convert the L and the C into the X. All right. So for L, the XL equals to what? 2 pi f times L. Right. And for C, because essentially the capacitance will be the shunt component of the transmission line. So what we need is the Y, so-called admittance. Admittance equals to 2 pi f times C. Okay? So you must multiply 2 pi f. This is certainly needed in the final exam. You cannot directly use L and C for calculation. You must convert them into X. But depending on the frequency, sometimes the 50 Hz, sometimes the 60 Hz. You must be careful reading the question. Understand what's the right frequency of the system. I think that is the only requirement for this type of question. Now look at the first one. We have this three-phase transmission line. Right? System frequency is 50, not 60. Please be careful. Then resistance is this value per mile. Okay? And the GMR is this value feet. And the conductor diameter is this value inch. Now, so far we have got three different length units, right? Mile, feet, and inch. So, of course, we finally convert them into meter. So in the final exam, I will give you the meter value. So, it won't be this feet and inch, mile. So, don't worry about that. But just for this tutorial question later on, 1 feet is 0.3 meter, 1 inch is 0.02 meter. So, that is, this one will certainly be given to you if needed. Okay? Calculate the resistance, inductance, and the series reactance and the capacitance, right? Shunt admittance, right? Per kilometer of the line. So finally, we have to convert all the values to kilometer, okay, to kilometer value. Now the permeability value is also given to you. Now clearly for this transmission line, they are unequal spacing, right? They are unequal spacing. So we have to recalculate the GMD, so-called geometric mean distance. So this is the given value, all right? So this one, resistance is, we have already converted everything into kilometers. Right? 1 mile equals to this kilometer. So the resistance will be this one per kilometer, this ohm per kilometer. Now let's look at the distance between these three phases. Right, A to B will be how much? 60 inch, 60 feet. Okay. The A and C will be squared root square of 10 square plus 30 square. Right. So this will be 31.6 feet. Now, after that, we can calculate the so-called, the GMR is also given already, right? So the radius is the diameter divided by 2, which is 0.598 inch. Then, because this is unequal spacing, so we have to recalculate the GMD, which is the third root of the product of the three distance values. So this is the GMD, right, in the feet value. Inch value. Now, if you use the same length unit, let's say inch or feet, it's also fine because essentially we are going to use the ratio between the GMD and the GMR, right? So you can see here, when we calculate the L, right? L equals to this coefficient times natural log of GMD over GMR. So if we both use the inch value, it's also okay. It's also okay because what we need is this ratio, right? Is this ratio. Now finally, L equals to this value, Henry per meter. But what is asked is Henry per kilometer. So you also need to divide by 1,000 to convert this value to be Henry per kilometer. Right? This is what's needed per kilometer value. Okay, per kilometer value. So this is L. Now, as I said, this is inductance. How about the reactance? Reactance is 2 pi f times L, right? Times 2 pi f is 50 hertz. So this is your reactance, 0.432 ohm per kilometer. Very straightforward. There is no difficulty. Just follow the steps. Right? Next is the capacitance. Capacitance, the equation is here: 2 pi epsilon divided by natural log of the ratio between GMD and R. Right? GMD we just calculated for this unequal spacing in the inch value, and the R is the radius. Right? Radius is 0.59. Okay, so this is your capacitance value in Faraday per meter. Right? And divided by root 3, you got the Faraday per kilometer. Okay, per kilometer. Then what's asked by this question is admittance. The admittance is 2 pi f times j and c. Okay. So everybody, please do not miss j. Okay. Do not miss j. So this is your admittance value. Okay. Admittance value. So that is this value. All right. 2.62 times this coefficient per kilometer. Okay, everyone, please be sure of this one, right? And for the capacitance, the reactance of the capacitance equals to 1 over omega c. Okay, that admittance is the inverse or reciprocal of xc, so that will be j omega c. Okay, so this one, everyone, please be careful about that. So that is the first question, very straightforward, because this is so-called single wire, okay, single wire conductor. Then question B is different. Question B is for the same spacing, each wire is replaced by a 4 bundled wire, right? We divide the original big wire into 4 small strands, okay, 4 strands. Now, what's the difference, right? The GMD, okay, the geometric mean distance remains the same. However, the radius will be different. The radius of the bundle. We need to recalculate the radius of the bundle, right? So after that, we just substitute the same value into the formula. So for this second one, because of this bundles conductor, right? You can see here, still the GMD remains, right? The GMD remains the same. Okay, GMD does not change. This is the 60, and this is the 31.6 feet. Okay. However, the resistance won't change either, right? Resistance is just the for each single wire, the resistance does not change. However, now you have 4. For each wire, you have 4 conductors. They are in parallel connection. So the resistance will be divided by 4 because they are parallel connected. Understand? And for resistance, if you have 2 parallel circuits, the total resistance is half. Now you have 4. So the resistance become 1/4. Okay, resistance become 1/4 because there are 4 conductors. Okay, they are in parallel connection. Now the GMR does not change. The radians is also does not change, and GMD does not change. Right, all are the same before. However, the GMR bundle will be changed because this is the 4 bundle conductors. So we have to update the GMR bundle value, which equals to this one. This one, everyone, you have to memorize because this is a coefficient and this is the item. Now after that, this will be your GMRB. B stands for bundle. Okay. Now after that, we still use the same formula, right? What you need to replace is the new GMR bundle value. Okay. GMD value does not change. So GMRB equals to this one, and this is your value, the Henry per kilometer of the L. And after L, we calculate the X just by multiplying 2 pi f. So this is your X value. and the GMR bundle has been changed because of the 4 bundled conductors. And then to calculate the capacitance, again we have to update the radius per bundle. Okay, so which is RB, you can RB equals to this one as well. These two formulas are the same, right? GMRB equals to this coefficient times this, and R bundle equals to this same coefficient times this item. These two items are actually the same. Right, so the bundled radius equals to this value. And after that, the capacitance, okay, the GMD does not change because GMD is for the 3-phase geometric distance between the 3 phases. And the radius for different bundles, different phases, the bundle value will be different. And so this is the capacitance, and this value divided by the natural log of the ratio. Alright? And so this is the capacitance Farad per meter, and then per kilometer. And finally convert it into Y. That is J omega C. Okay? So this is your admittance value. You can see that the whole calculation is just standardized. You calculate GMD, GMR, and if it's a bundled conductor, you recalculate the GMR for the bundle. Okay? And if it's unequal spacing, you calculate the GMD. That is substitute these formulas. Any questions for this one? What you need is to, just memorize these different formulas. They are straightforward. Try to understand the rules behind. Any questions for the first two? Okay. Differences is that second one is a bundled conductors. Okay. Now, if no questions. No questions, we move to 5.2. Okay, 5.2. 5.2, a 3-phase transposed transmission line is composed of one ACSR conductor per phase with a flat horizontal spacing of 11 meters between adjunct conductors. So here you can see we don't have the layout of the 3 phases, but we are given this specific information, flat horizontal spacing, which means the 3 phases are kind of placed in the same horizon, and the adjacent distance is 11 meters. The conductors have a diameter of this value and GMR of this value each. The line is replaced, okay, by this. Originally it's a single bundle, right? Now it replaced by 3 bundles, 3 conductor bundle, and having a new diameter, new GMR. Then the replaced line will also have the same flight horizontal configuration, but it operates at a higher voltage. Therefore, the phase spacing is increased to 14 meters between the adjunct bundles, and the spacing between the conductor bundle is 45 meters. Now, determine the percentage change in the line of inductance and capacitance. We have read so many words and text. What does that mean? Basically, 2 scenarios, right? First scenario is a single bundle conductor with these parameters. Second scenario is a 3 conductor bundle with new parameters. Then we are going to compare the inductance and the capacitance. That means you need to calculate it twice using 2 different parameter sets. Right? This is what this question asked for. Now, we don't have the layout of the 3 phases, but since it's a flat horizontal placing, so everyone you can immediately draw this, right? So they are in the same horizon, they are flat, and the adjacent distance 11 meters, okay? And GMD, of course, this is unequal spacing, so GMD equals to the third root of the product of the 3 distances, right? 11, 11, and then 1 to phase A to C is 12. So this is the GMD. Now GMR is also already given, right? GMR is already given. The radians is also given. Although we have the diameter, so the radians is half of the diameter in centimeters. Okay, note that we have to later on we need to convert everything into meter. Okay, into meter. And so L equals to this item times natural log of GMD here divided by GMR. Okay. Now note that very important. GMD is in meter, and GMR also should be in meter. But here GMR is centimeter, so you have to convert it into meter value. I think that is only like a challenge for you because you need to be careful about the units. Okay, units. Sometimes they are given in centimeters, sometimes kilometers. But in the end, you have to unify them into meter or kilometer because they are only calculating the ratio, so they must be the same units. Understand? So that is, so after, since this is a meter, so finally this value is also Henry meter, okay? It's always Henry meter because of this coefficient, okay? This always the unit is Henry per meter. And of course, the capacitance is the same, right? This equation, GMD over radians. Once again, radians is meter, GMD is, radians is centimeter, GMD is meter, so you need to convert this centimeter to meter. Finally, this is a Faraday per meter. This is also the unit, okay? Also the unit. So this is the original value of LC for the first case. Second case, we replace this conductors with three strings, okay? And then we extend the distance to 14 meters. And the new distance, the distance between the bundles is also given, which is 45 centimeters. And what will be the new L and C? We just recalculate, right? GMD will be the same formula, third root of the three products. But now here, D is no longer 11, D becomes 14. Okay, as the question tells you, D becomes 14. So 14 times 14 times 28. This is your new GMD. And the GMR bundle, okay, this is the bundle case. GMR is, this is a three string bundle, so that equals to this one, which is this value, centimeter. And the radians per bundle, okay, radians bundle just equals to this formula. This smaller d is 45 centimeter, so this is your RB, okay, so this is RB. Now, we have the new value set. Substitute them into the same formula. Okay, the ratio for L and also this ratio for C. After all the units will be Henry per meter, Faraday per meter. Okay, so essentially the same as the previous question. Okay, you just note the three strengths bundle case. Okay, recalculate the GMRB and so-called RB. Now after that, we just compare this old LC and the new LC and see the percentage change. That is what the question asks. The percentage change will be, right? Now, the new L minus old L divided by the old L increased by how much? 27. Decreased by 27. Then the C, okay, new C minus old C divided by the old C increased by 35%. So you can see that after we do the bundled conductor, we can significantly reduce the reactance. However, because we have longer spacing, then the capacitance has increased. Capacitance has increased. Any question? Any questions so far? Just to apply the formulas. let's move to 5.3. Okay, 5.3 is like a combinational question for calculating the parameters and also the so-called transmission power, transmission current. I remember 2 years ago, one of the final exam question is very similar to this one. Okay, 2 years ago. So please be careful about this question. So basically, you can see here we are provided with these values, configurations. So of course, the first step is to calculate the line parameters. But after that, you can see we are given this load and this so-called pi model voltage, and we are going to determine the receiving end voltage, current, and the complex power. So that means we are going to use the so-called transmission matrix ABCD, right, or the pi model. As I said in the final exam, okay, this transmission matrix ABCD coefficient are very complex to memorize. So I will give it to you if needed. Okay, so for transmission matrix, no need to memorize. That is the only, not only one, but one of the formulas that you don't need to memorize. Okay. Let's see. Okay, so this one is also a flat horizontal placing. This is 40 meters, diameter, blah 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 blah, everything. Okay, so first of all, let's calculate the. This is a 4 bundle, right? The 4 bundled conductors. Now this is a flat spacing. Okay, flat spacing. 4 bundles. All right. 14 meters, 14 meters. So then phase A to C will be 28 meters. Now immediately we can calculate the GMD. Right, GMD actually equals to how much? 14 times 14 times 28, the third root, that is 17.6. Okay, so that is the GMD. Okay, that is the GMD. And because this is a 4-string bundle, so we have to calculate the GMRB. Okay, that equals to this one for the 4-bundle case. Always you times 1.09. This is the coefficient, and depending on the number of the strands, you use the different one. Like this is 4 bundle, right? And the third 3 bundle is like this is also 4. The 3 bundle is like this. Okay. We're trying to compare these 3 strands and the 4 strands. Okay. Then after that, you calculate the new GMR bundles value. That is in the centimeter because the original B and the GMR are in centimeters. This value will be unit with centimeter. So after that, what is L? L equals to, this formula, right? This one you have to memorize, of course. GMD over GMDB over GMRB. Okay, GMD does not change. GMD just measures the distance between the 3 phases. So finally, this is the L. Okay, unit is Henry per meter. Then for the entire length, okay, this is the per meter value, right? What is the total length? Total length is 400 kilometers long. So you need to times this value with 400 kilometers. So the total inductance is this large. Okay, is this large. And of course, later we need to convert it into X, alright? Now how about the C? Okay, C equals to this one. You have to recalculate the bundled radius. This is the 4 bundles case, so this will be your new RB. And substitute this RB to here. And GMD already calculated 17.6 meter. Okay, everything. After that, this is your Faraday per meter. Faraday per meter. And once again, this is the per meter value, so you have to times 400 kilometers. So this is the total Faraday capacitance. Now, once again, what we need is X, right? So for the transmission line here, we don't have the resistance value. Resistance is ignored. Right? There is no information about the resistance. That's why it's assumed the line to be lossless. That means there is no resistance. Okay? So the total impedance, right, equals to J omega times X. Okay? This is the X. And how about the Y? You know, in the end, we are going to use Y as pi model, right? We're have to memorize this pi model. Pi model in the series section, that is Z, and for the two shunts, each will carry half of the Y. Each will carry half of the Y. So now, what is the Y? Y equals to J omega times C. So this is your Y, and each will carry half. So just there. Now, next question is to determine the power, the voltage, and this voltage, right? So it is a circuit analysis question, right? For all the calculation, we have to use the per unit value. So after we have the original real values of the electrical parameters, we need to convert them into per unit, right? So we select this VV and this SV. Once again, in the final exam, this VV-SV will be, pre-selected for you. And with VV-SV, you calculate the VV and also the IB, right? So this is our base value set. And then in per unit, let's convert this Z and Y into per unit, right? By just dividing them. Z equals to Z, real values divided by ZB, okay? And why is interesting, okay? Theoretically, Y's per unit equals to Y's real value divided by Y's base value. But we don't have Y's base value. What we have is Z's base value. Now, what's the relation between Z and Y? It's a reciprocal, right? So, divided by YB means you times ZB. That is the interesting part. Okay? That is the interesting part. You must understand Y and Z, the relationship is the reciprocal. Alright? We have ZB. Now what is the YB? YB is just a 1 over ZB. Right? Then so for Y over YB equals to Y times ZB. That is 1 point. Okay? You have to understand. Now, after that, this is your Y, right? This is your Y. Okay, this is your Y. And now everyone, after that, you can mark the values to this pi model. You can mark the values to the pi model. Then, okay, we are given the input voltage and the current. What will be the output current and voltage? Let's just use ABCD matrix. Now, as I said, this ABCD matrix formula will be given to you. You just substitute this ZY into it, right? For pi model, A equals to D. This one will be given to you, don't worry. Just substitute the values to it. A and D will equal to this one. And B equals to this one. C equals to this item, this one. So finally, ABCD matrix will be obtained. ABCD matrix will be obtained. That is this one. Alright? That is this one. Okay, with ABCD matrix, then things will become much easier. Calculation will be much easier, right? So here, determine the receiving end voltage, blah, 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 blah. If this value are being transmitted. So that means this will be your input, right? This will be your input. Once again, these values are all in real values. These are all in real values. So we convert these real values into per unit values again. This is your V, this is your S, okay? This is your current, so everything becomes a per unit value, right? According to the transmission matrix, Vs, Is equals to ABC times VR. So what we know is like we know VR and IR. We are going to calculate Vs and Is. Yeah. We know the receiving end voltage. We are going to calculate the sending end voltage. So this VRR equals to the inverse of ABCD matrix times Vs Is. Okay. Now what is the inverse of this one? Here. Now this one, it's also a basic formula for the matrix operation. This is inverse of ABCD. I'm not sure whether you are able to memorize, but if not, I think we can also provide you with this formula to calculate ABCD inverse. Then after that, okay, so VR and IR can be directly calculated. So this is our inverse. Okay, this is our inverse matrix, and this is your specified sending voltage and sending current. So you can calculate your receiving voltage and receiving current. Okay. or what? Complex or not? The key is like as long as you get this transmission matrix, then the calculation is much easier. But the transmission matrix, is a function of the electrical parameters. That's it. That's the information you want to understand. Now, this is per unit, right? V and I, and how about S? S equals to V times I's conjugate, that is this value, right? And you can write it in the phasor format or rectangular format, respectively corresponding to P and Q. Okay? And of course, you can convert them into into real values, right? V times VB, I times IV, S times SB, right? Everything you can convert them into real values. And of course, you can also calculate the power factor because you already know the P and Q and S. You can calculate the power factor and also the power factor amplitude. Okay, you can see that this Q is positive. That means it has a positive angle. S will have a positive angle because this is a positive. That means it's lagging. And that means it's lagging. Okay. That's a question A. Question B. If the line is energized with void at the sending end, when the load at the receiving end moves, what does that mean? That means the sending voltage is this value, but there is no load. I receiving IR equals to 0. Right? Still, you can see here IR is 0, right? According to this one, Vs equals to A times VR plus B times IR. Then IR is 0, so this one will be 0. So Vs just equals to A times VR. Right? V of A's coefficient we already know. So we know Vs. Vs is maintained at this value. This is 1.0 per unit. This A coefficient is this value. So VR just equals to Vs divided by A. This is your VR. Per unit. The actual value is multiply it with AB, you get this. And the second one is straightforward. Let me summarize. The key for this transmission matrix is that we calculate the electrical parameters. Right? After that, we use this formula to get ABCD. Once you get ABCD, the relationship between the input and output can be quickly calculated. It depends which is known, which is unknown. If this is known, then you directly use this one. If this is known, then you need to use the inverse of this. Just the basic operation of the matrix. But don't worry about this part. This formula will be what you need to worry is about this line parameter calculation, right? Number one, formulas you need to memorize. Number two, the so-called bundled conductors you need to understand. Number three, the unit. You have to use unified units, centimeter, meter, kilometer. Be careful about the question setting. And finally, note that all the calculated values for L and C are value per meter, okay? Because of this coefficient. This is Henry per meter. This is a Faraday per meter. Okay, so these two you must understand. Then you convert them into per kilometer value, but that is per kilometer value. So for the power grid, power transmission line, you know the total length, then you get the total value. Understand? This is the per meter value. Okay, that's the unit value. And for this 400 kilometers long, you times 400 kilometers. Okay, kilometer, this is a meter, okay? So please review this part. I mean, the key is to be careful, that is the requirement. Okay, any questions? I think this part is the simplest one for the full lecture. Any questions? Yes, it's a so-called two-part network. Right?
It's always
Yes. V and I, the two parts. Any questions?
Also, if ESI is given, we use the inverse.
Yeah.
And if it's not given, then we use the
Inverse, yes.
non-inverse.
Yes.
Okay.
Okay, if you have no questions, we can finish earlier. And you probably have received the email asking for student feedback, and please take some time to fill the student feedback. Thank you. And also be reminded of the Oasis quiz next week. Next week during tutorial session, go to the lab and do the Oasis. The scope, okay, the scope of the Oasis quiz is until transmission line. Okay, the fault analysis will be excluded. This afternoon during the lecture we will cover the fault analysis, but it won't be included in the Oasis quiz. But in the written quiz, I mean after the recess week, everything will be included. Understand? The Oasis quiz only P1, P2, P3. All right, we